Okay, let us now talk about, and to wrap up phasor analysis, the six different quantities of interest. For impedance, Z, it's equal to the resistance plus capa- plus reactance. So this is resistance, and this is reactance. And you can encode this a little more by talking about the case of what kind of element might be present. Maybe an inductor, maybe a capacitor. Both of these in series, of course. But another related phenomenon, which becomes more important in EE3030 in under two-port network modeling, or just in general for talking about current dividers compared to voltage dividers, is admittance. So what is admittance? Admittance, denoted by the symbol Y, is equal to 1 over Z. So sometimes it is easier to talk about admittance compared to impedance. And to give you an example of this, maybe you're talking about how easy it is for current to flow through a wire, or how easy it is, or how hard it is for current to go to another path. This has good admittance, similar to talking about conductance. It has good conductance. Good conductance. Whereas this one is, and when you're comparing it between these two, has bad conductance because you can't really make current flow through an open circuit in ideal situations. Of course, a little bit does happen due to electromagnetic interference, which you'll maybe talk about in EE3050. But for the scope of circuit analysis, we omit those details. That's the idea of admittance, just kind of like how easy it is to admit current, hence the name admittance. Now, I want to expand this a little bit further. 1 over r plus jx. We use the complex conjugate, and we get the following. R minus jx divided by r squared plus x squared. So we get r divided by r squared plus x squared plus j, apologies, minus divided by r squared plus x squared. This quantity is called conductance. While this quantity, including the negative, is called susceptance. So we have to kind of summarize these terms. Y is equal to G plus JB, where we get the following. Or if you want to think about it like this, G minus JB. But just to keep things consistent, we usually use a plus, where G is equal to R divided by R squared plus X squared. And then B is equal to negative X divided by R squared plus X squared. Okay? So that's the different quantities, and there's 6 of them in total. So let's talk about the 6. Impedance. It's denoted by the symbol Z. Related to it is resistance, denoted by the symbol R. Reactance, denoted by the symbol X. Admittance, denoted by the symbol Y. Conductance, denoted by the symbol G. And susceptance, denoted by the symbol B. This is related like so. This is related like so. And then to relate once more, we have r divided by r squared plus x squared. And this is x, negative x, divided by r squared plus x squared. Now, the units for admittance, conductance, and susceptance is Siemens, or the unit capital S. The units for impedance is ohms, or omega. And that's the 6 important impedance and admittance quantities. Now, just to talk about why you would care about admittance, conductance, and susceptance, as mentioned before, sometimes it's easier to talk about how good something conducts rather than talk about how good something is resistive, because sometimes we might not get a good idea. So, and the other important part is two-port network modeling. We use it all the time with T models, H models, so on and so forth. It's kind of very fundamental just to talk about these 6 quantities. And you'll see a lot of them in E3030 when we are talking about two-port network modeling. But just in general, sometimes it's easier to find voltage current relationships in terms of admittance quantities compared to impedance quantities. An example is like this. Sure, this is easy to find the impedance of, but sometimes it's easier to find the admittance of and then find the reciprocal. Okay, so thank you.